Welcome. In this lesson, we are going to learn about the fifth shortcut, hypotenuse-leg, for proving triangles congruent. We know we have, we have side congruence. We have side angle side congruence. We have angle side angle congruence. We have angle angle side congruence. And we're going to learn about HL congruence. So we talked about how side-side angle, or its evil twin, angle angle side, how that is never a reason to prove triangles congruent. Okay, and the reason is because if we look at our two triangles right here, if we say, hey, are these two triangles congruent? Well, here's the thing with this. We have this angle is limited, this side and this side. These three pieces are all limited to be congruent. But the difference here is we have no limit on this angle up here. And therefore, this entire side can be a different length in each of these. And so these triangles cannot be congruent. All the other patterns we have, side, 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 angle, side, and so on, they either are limited by an angle or by a side, so they're forced to be the same shape. But because we don't have that top angle and we don't have the side that's opposite it, that's across from it, congruent in these two triangles, they could be different lengths and it wouldn't break the idea of having an angle aside and a side congruent. This is why SSA or ASS does not prove triangles congruent. But we do have a situation where SSA does work. Here's the thing, it's in a really specific case. Okay, that is when the A on the SSA, okay, or ASS, okay, where that is a right angle. So if you have a right triangle, because this is forced to be 90 degrees, because of that, then it forces the other angles to add or be the difference to 90 degrees, because again, if one angle is 90, the other two can only be 90 together because they have to add to 180. So it forces them to be congruent. So let's talk a little bit about some vocabulary here. So we have a right triangle. So if we're talking about a right triangle, it's a triangle that has one right angle. The hypotenuse is the longest side. It's always across from the right angle. So we call that side the hypotenuse. Again, no matter how we turn or twist this right triangle, the hypotenuse is always the side that's across from it. Again, the longest side. It will always be the longest side. The legs are the other two sides. They're the sides that make the right angle. Okay, so when we talked about, like, for instance, to give an example of sides, so we talked about an isosceles triangle, how the legs were the congruent sides, and the base was the side that wasn't. Okay, so this is kind of similar situation. It's just that now we're talking about a hypotenuse and legs. So because of this, we call this HL, and we'll abbreviate it as HL congruence. So this is our fifth one. If the hypotenuse and a leg of one right triangle is congruent to the hypotenuse and leg of another right triangle, then the triangles are congruent. Now again, it's saying the hypotenuse. Okay. So again, we're saying here it is, the right angle, they're both right triangles. We have a leg congruent and we have the hypotenuse congruent. So it is the pattern ASS, which again, we don't write that because it only works in right triangles. It won't work in other types of triangles. So again, if I had segment AB and segment DE congruent, and then AC and DF, which are the hypotenuse congruent, and these are right angles, then these would be congruent, these two triangles, by HL congruence. So let's take a look at this, at the pattern we have here. And this is where, and I haven't emphasized this, and I'm going to right now, that the right angle cannot be the included angle. Now, if you remember what included means, is that if I have a triangle, so let's just do an example here, and we mark two of the sides. So I'm just looking at these. Now I know I'm only looking at one triangle here, but I did a triangle like this. The included angle is the angle that's between the two. The other two are the non-included angles. So here's the deal, okay? If we're going to use HL, okay, it has to be one of the right angle has to be one of the non-included angles. So in other words, what I'm saying is if we look at part A here, or part A, first one here, you see how we have this side's 3 and this side's 5. This right angle is between them, it's included. This cannot be HL. It cannot be HL. Here you have the hypotenuse. On the third one, you have the hypotenuse. You have one of the legs, and it's a right angle. Okay, again, if you're going to use HL, it is the pattern angle side side. Okay, so that means that it cannot be the angle that's between them. If we were going to use anything for this first triangle here, if we're going to use anything for this, then we would have said that this would be side angle side, because it's the 3 here and the 5 here, and then obviously these patterns wouldn't match, and so this is not. Now these are both ASS. Okay, again, we don't call it that because it doesn't work in every case, so we say it's HL congruence for these two, because it's the hypotenuse, it's the leg, and it's a right triangle. So which of the following triangles are congruent by HL? Again, it's got to be the pattern, angle side side, but in a right triangle. Has to be in a right triangle. Okay, so you're looking for that pattern. Why don't you take a moment, look at these 4 different situations. I'll give you the answers here shortly, but why don't you take a moment to try it on your own? Okay, so here are your answers. So let's look at the first one. You can use a reflexive property to mark RT congruent to itself with the double mark that I put on there. We also know that if RTU right here is a right angle, then RTS also is a right angle. So we have those right angles, we have a leg marked, and we have the hypotenuse marked. They are the pattern angle side side, okay, for both of those. Again, and it's only if it's angle side side and it's a right triangle. In this case it is, so it's HL, it's yes. Number 2, these are both right triangles. They are both angle, again, angle, side, side, angle, side, side. So it is also HL for number 2. Number 3, you can mark reflexive property. They share that middle side there. Again, they're right triangles and it's the pattern angle, side, side, angle, side, side. Okay, so it's HL again. Now, here's the deal with this one. You got to be really careful. We can look at this entire triangle right here, and it's an isosceles triangle. Now, something that we learned last section or whatever is that if I have 2 sides congruent in a triangle, then the angles opposite them are congruent. So this angle at B and this angle at D, they're congruent because these sides here and here are congruent. Here's the thing though. Here's the thing, okay? And we know the reflexive property here. So we do have the pattern angle side side, but we cannot assume this is a right angle here. You cannot assume that. So this is a no, because we have no limit on the length, these angles right here at A. And because there's no limit on that, these lengths here and here have no limit, which means these, we can't say for sure these are congruent. So again, even though this is the pattern ASS, okay, we don't know it's a right triangle, so you cannot say, okay, you cannot say it. Okay, so we have some given information and a picture. Now, if you remember back to our steps, mark all you're given on the picture, then mark everything we know from the given that we can add to it. Then after that, Then mark down anything we can infer from the picture, okay? And then we're going to look at trying to prove these two triangles congruent. So first off, QPR and SRP, they're right angles. So you can do a right angle there. So we know they're congruent to each other. We also know that QR is congruent to SP. So we can put a tick mark there. So this is all the information we have. We can't add anything else other than the reflexive property here. So when we start adding things that are extra, that are based off the picture, we need to actually write it out. So the segment PR is congruent to the segment PR. And your reasoning for this is reflexive property. Okay. So now if we look on here, we do have the pattern angle, side, side. Okay, angle, side, side. And this is a right triangle. So it's going to be triangle SRP is congruent to triangle QPR. And the reasoning is HL congruence. All right, here's another proof. Given T is the midpoint of RV. Now, now remember your steps. Put all your given down. Then once you have your given down, you want to take anything that you can take from your given and add it to the picture. And then you want to go ahead and mark any of the obvious things that are on the picture. So like vertical angles, if you have parallel lines, things like that. Reflexive property, if that is on there. Anyway, all right. T is the midpoint of RV. Well, if T is the midpoint, then I know that RT is congruent to TV. So you can say that. And in fact, I'm going to write it. RT, because it should be written, is congruent to TV. Now, how do we know that's congruent? Because we added it. Well, it is in the given, but we applied a theorem here, and that's the definition of a midpoint. I know I'm just writing def midpoint, but yeah, you can do it that way. I also know that S and U, angle S and angle U are right angles, they're already marked. And I know that the segment RS and the segment TU are congruent, and it's already marked. Now, again, you clearly see the pattern, angle side, side on both of these. Well, again, angle side, side is only a valid method if it's a right triangle. Okay, so on here, we actually can say triangle RST is congruent to triangle TUV, and the reason you can do that is because it's HL. Again, angle side side. Only way you can do it is if it's a right triangle, so we call it HL. Think about your steps for this proof. The segment BE bisects the segment AD at C. So BE cuts AD in half. So again, you want to say that the segment AC is congruent to CD, those two segments, and that's the definition of a bisector. Okay, definition of a bisector, or definition of bisect, however you want to write that. We also know that AB and BC are perpendicular, so that's a right angle there, those two segments. I know that DE and EC are perpendicular, so that's right. Again, remember that upside down capital T means perpendicular. Okay, so when we have it there and there. I also know that AB is congruent. I'm going to do a double tick mark because I already used a single to segment DE. Okay, now some things we could add to this picture. Now you don't need it. We actually have enough information to prove these triangles congruent, but I'm going to think that for some of you, you're going to just do it because hopefully it's second nature, right? And hopefully it is that we know that these angles are congruent because of the vertical angles theorem. So again, if you're going to mark it on the picture like that, you're going to, just like we did with the segments AC and CD here, okay? So we need to write this out. So ACB, that angle is congruent to angle, and remember, you can flip this first and last letter. It doesn't matter. So I could call it DCE or ECD. Okay, and that's a vertical angles theorem that they're congruent. Now, because we have this, you actually have enough information to use a couple different things. You could use on here, you could use angle side congruence because that's there. All right, so you could use that one. You could use your HL because again, they're right triangles with the pattern hypotenuse leg. Okay, so you could do HL for this as well. So you had a couple possibilities for this. But anyway, so we know that triangle ABC is congruent to triangle DEC. And the reasoning is, you take your pick. It can either be angle side congruence, and it can actually go two different directions with that, or it can be HL congruence. All right, so I would like you to go through these, and I want you to determine whether there's enough here to prove these congruent. Now, when it says explain your answer, again, you're using, side, congruence, side, angle, side, angle, and then HL. So you're using those reasons to explain. But also what I would like you to do to get in the habit of this is if, say, for instance, on number 9, you're going to mark AD congruent to itself because the two triangles share it. So you want to say segment AD is congruent to segment AD by reflexive property. So my expectation is that you're writing out everything you add to your pictures. So you're going through adding and you're determining, hey, can you use one of our 5 ways to prove that? So take a moment to do that. So I know this is a lot to look at here. I want you to take some time kind of going through and looking at each question individually. I'm going to do like some of the highlights of these. So for example, let's look at number 11 on here. Okay, so when I'm looking at this question, we have in here, and it's not the easiest to see, but these are parallel lines here. And so because of that, you know that you have, corresponding alternate interior, alternate exterior, same side interior, supplementary. So we know that angle S and U are congruent because they're alternate interior. So what I wrote here is that U and S and then R and T are congruent. You also know vertical angles there in the middle at O. Again, don't call it angle O, it's ROS and UOT. So we actually have, the segments that are already marked. We actually have all the corresponding angles. So you can use, you could do angle side or angle side angle. Remember, there is a side, but there's not an angle, so don't try that. The other one that I want to point out here that I think is a big deal, other than a 10 and the last one, I guess it's number 6, 10 and 6 being no's, is number 5 in here. See how I had to pull the two triangles apart? That is helpful to do. So sometimes you may want to do that. If you have something overlapping like that, pull them apart. Now they still share that bottom side. So it is the pattern angle side. But again, pulling apart makes it easier to see the two triangles you're using there. Okay, so now tying it all together, we're trying to solve for the missing variable in each case, x, that'll make them congruent by HL. Now remember what HL is what we're trying to show is two triangles congruent where two right triangles congruent where it's a leg being congruent and it's the hypotenuse congruent. So again, identifying the hypotenuse is important. In fact, one of the things that sometimes I do is I go through and I'll like circle like, oh, well, this 17 is opposite the right angle, that's the hypotenuse. So then the x is opposite the right angle, it's the hypotenuse. Okay, so sometimes I go through and I just kind of identify the hypotenuse in each of these. Again, the side opposite the right angle, because it helps you know, again, hypotenuse is going to be congruent to hypotenuse, leg to leg, and so on. So take a moment and try to solve for x in each of these cases. I'll put the answers up, pause the video now. All right, here are your answers. Again, I went through, and I do this because it even helps me. I mean, you can make a choice on your own what you want to do, but I actually physically circle the hypotenuse in each case. So number 7, I'm circling the 17 and the x. Number 8, the 4.25. Number 9, the 13 and the 4x plus 1. Number 10, the 2x plus 1 and the x plus 3. So again, we're setting those equal then, and we're just solving is all you're doing. So once you get them equal to each other, your geometry is done, and it's just more algebra. And you can check your math against my math.